Hello students, in the previous session we studied about how to apply integrals to calculate area below the simple curves. Regarding this, there is a remark: in case of symmetrical closed area, find the area of the smallest part and multiply the result by the number of symmetrical parts. Now, let us look into an interesting example here. Find the area under the curve y is equal to x to the power 4 and the lines x is equal to 1, x is equal to 5 and the x axis. For the solution, the given curve is here y is equal to x to the power 4 with x axis and y axis, and the ordinates x is equal to 1 and x is equal to 5. Therefore, the required area is equal to area of the region A, B, C, D, that is equal to integral 1 to 5 y into dx, that is equal to integral 1 to 5 x to the power 4 dx, that is equal to x to the power 5 upon 5 with limits 1 and 5. On applying limits, we have 1 upon 5 into 5 to the power 5 minus 1 raised to 5, that is equal to 1 upon 5 into 3125 minus 1. Therefore, the required area is 3124 upon 5 square units. Another example here: find the area of the region bounded by x square is equal to 4y, y is equal to 2, y is equal to 4 and the y axis in the first quadrant. For the solution, the given curve is x square is equal to 4y, which is an upward parabola with vertex at the origin 0 0 and y is equal to 2 and y is equal to 4 are the lines here, and we are supposed to find the shaded area A, B, C, D. Therefore, required area is equal to area of region A, B, C, D, that is equal to integral 2 to 4 x into dy, that is equal to integral 2 to 4 2 into square root y into dy, that is equal to 2 into y to the power 3 upon 4 upon 3 upon 2 with limits 2 and 4, that is equal to 4 upon 3 into 4 raised to 3 upon 2 minus 2 raised to 3 upon 2. On simplification, we have 4 upon 3 into 8 minus 2 root 2. Taking out 2 as common, required area is 8 upon 3 into 4 minus square root 2 square units. Now, let us look into the area of the region bounded by a curve and a line. Here, we will learn to find the area of the region bounded by a line and a circle, a line and a parabola, a line and an ellipse. Let us see an example here. Find the area of the region bounded by the curve y is equal to x square and the line y is equal to 4. Now, for the solution, since the given curve represented by the equation y is equal to x square is a parabola symmetrical about y axis only, therefore, from the figure the required area of the region A O B A is given by 2 into integral 0 to a x into dy, that is equal to 2 into area of region B O N B bounded by the curve y axis, the lines y is equal to 0 and y is equal to 4. This is the shaded area we need to calculate with width dy and height is x. Therefore, 2 into integral 0 to 4 x dy is equal to 2 into integral 0 to 4 square root of y dy, that is equal to 2 into 2 upon 3 into y power 3 upon 2 with limits 0 and 4. On applying limits, we have 4 upon 3 into 4 power 3 upon 2, that gives 4 upon 3 into 2 power 3, that is equal to 4 upon 3 into 8, that gives 32 upon 3. Here we have taken horizontal strips as indicated in the figure to calculate the area. Now, let us look into one more example. Find the area of the region in the first quadrant enclosed by the x axis, the line y is equal to x and the circle x square plus y square is equal to 32. For the solution, the given equations are y is equal to x is the first equation here and x square plus y square is equal to 32 is the second equation. We have in the figure a circle with x axis and y axis and a line y is equal to x. We also have vertex A as 4 root 2 comma 0 and B as 4 comma 4. We drop a perpendicular BM on OA. Solving these first and second equation, we get the line and the circle meet at 4 comma 4 in the first quadrant. Now, after drawing the perpendicular BM to the x axis, the required area is equal to area of the region OBMO plus area of the region BMAB. Now, the area of the region OBMO is equal to integral 0 to 4 y dx is equal to integral 0 to 4 x dx, that is equal to 1 upon 2 into x square with limits 0 and 4 is equal to 8. This is the third equation. Now, again the area of the region BMAB is equal to integral 4 to 4 root 2 y dx is equal to integral 4 to 4 root 2 square root of 32 minus x square into dx, that is equal to 1 upon 2 into x square root of 32 minus x square plus 1 upon 2 into 32 into sine inverse x upon 4 root 2 with limits 4 and 4 root 2, that is equal to half of 4 root 2 into 0 plus half of 32 into sine inverse 1 minus 4 upon 2 into square root of 32 minus 16 plus 1 upon 2 into 32 into sine inverse 1 upon root 2. On simplification, we have 8 pi minus 8 plus 4 pi, that is equal to 4 pi minus 8. This is the fourth equation. Now, adding equation 3 and 4, we get the required area as 4 pi square units. Now, another example here, find the area bounded by the ellipse x square upon a square plus y square upon b square is equal to 1 and the ordinates x is equal to 0 and x is equal to a e, where b square is equal to a square into 1 minus e square and e is less than 1. For the solution, the required area of the region BOB dash RFSB is enclosed by the ellipse and the lines x is equal to 0 and x is equal to AE, which is shown in the figure here. Note that the area of the region BOB dash RFSB is equal to 2 into integral 0 to AE y dy is equal to 2 into b upon a integral 0 to AE into square root a square minus x square dx, that is equal to 2b upon a x upon 2 into a square minus x square plus a square upon 2 sine inverse x upon a with limits 0 and AE. On applying limits, we have 2b upon 2a into AE square root of a square minus a square e square plus a square into sine inverse e. Therefore, the required area is AB into e into square root of 1 minus e square plus sine inverse e. One more interesting example here. Find the area of the parabola y square is equal to 4ax bounded by its lattice rectum. For the solution, from figure, the vertex of the parabola y square is equal to 4ax is at the origin O, and the equation of the lattice rectum L S L dash is x is equal to a. Also, parabola is symmetrical about x axis. Therefore, the required area of the region O L L dash O is equal to 2 into area of the region O L S O, that is equal to 2 into integral 0 to a y dx, that is equal to 2 into integral 0 to a square root of 4 a x dx, that is equal to 2 into 2 square root a integral 0 to a square root x dx, that is equal to 4 root a into 2 upon 3 into x power 3 upon 2 with limits 0 and a. On applying limits, we have 8 upon 3 into square root a into a power 3 upon 2, that is equal to 8 upon 3 a square. Here students, there are some questions for the home assignment for you. Question number 1. Find the area of the region bounded by the curve y square is equal to x and the lines x is equal to 1 and x is equal to 4 and x axis. Question number 2. Make a rough sketch of the curve y is equal to x square with x lying between 0 and 3 and determine the area bounded by the curve x axis and x is equal to 3. So, students, in this session we solved some examples using integration to calculate the area under the curves. In the next session, we shall learn how to calculate the area between two curves. Hope to see you with your home assignment in the next session. Thank you.